Okay guys, let's start. Today we'll change the topic. Okay, we still remain with the internal forces. However, we can look at a new kind of structure. Okay, that kind is called the pin jointed truss. Okay, the name suggests that all joints are pin. Okay, we will see the implication later. In Thai it's called krong thak. Okay, so you know the wording. Let's go through first, because these are more kind of like special kind of structure. It's not like the normal beams that we look at, not the normal frames we look at. Okay, so first we'll talk about the type, the example of it. What kind of structure we call pin jointed truss. By the way, you done dropping things yet? By the way, sometimes they just call them truss, right? Leave out the word pin joint. Okay, we'll see example of it. Then we talk about the definition. How do we call it, and when do we call it pin joint? When we call it truss. Okay. Then we will discuss the internal force. Okay. Well, this suggests that, and in fact, it is not the same as what we have done before. Okay, how different we will see, and then we talk about how we analyze them, the method of analysis, of course, how we analyze them, and then we see example. Okay, let's see what type of structure do we look at. Well, usually the pin joint truss is very suitable for a very long span structure. For example, this kind is a bridge. Here, on the top here, actually is the pin joint. What happened is the pin joint rests on the columns, and the floor, or this floor, actually hang on to the structure of the pin joint truss. Okay, so in effect, it means that for this bridge to stay, the main column, the main structure will be the column, and then the pin joint truss. The road we run on, the pavement we run on, the car run on, is actually rests on the pin joint, not the pin joint truss rests on the pavement. Okay, that is another bridge. I think that is Sapan Kung Thon, that is Sapan Put, I think. Okay, at least when I downloaded it from the internet, it said so. If not, my apology. Another type is the roof truss. This roof usually is on, say, like the gymnasium. Right? You go up to the canteen, KFC, right? And then you look on the top. There's a gymnasium on the top. Then if you look up the truss, you will see the steel structure. That type is also truss. Okay, this is the kind of the truss for the roof. Again, it's very suitable for a very long span, right? Because a gymnasium, you need, say, like a basketball field inside it, right? You need huge space. You cannot have column in the middle of the basketball field, correct? So this is a very long span. Because the way we transfer the load, the height of the truss will help absorb more forces. Okay, we'll see in the pure mechanics in the next course. Okay, this one we just study the general behavior first. Now let's look at the small joint here. This is a type of the joint. Okay, that one there is what we call rivet. Okay, that one is a bolt. Okay, this kind of joints, they do not use the welding. The welding is too rigid. The word pin joint suggests that it should be able to rotate about the joint, right? Connected by pin. So be careful with that one. Another type, it will be like that. That is again rivets. Okay. The idea is that to make it, or at least once you do not weld it, you just bolt it in together, it can move slightly. Okay. That is simulating the ability to rotate. In our design, that is the way we look at the joint. The all force, the line of the member will go meet in one point, at one point. Okay, And if you take moment of that point, you will always get 0 equal to 0, meaning it can rotate freely. It won't rotate because it will be connected with something else that's stopping it from rotation. But by concept, the joint in itself can rotate, cannot stop rotation. Okay? Now, when we draw it, we tend to draw it that way, right? These are the members. The back line here are the members, okay? The circle here, as usual, is the pin connection. Okay? Now let's talk about definition first. We have to define how we call them pin joint because there will be special things happening. First of all connection must be pin type. Okay? What does it mean by pin type? The word pin type actually meaning it allows rotation. Pin support doesn't stop rotation. Pin joint doesn't stop rotation, right? Therefore, in terms of support, you also have pin support and roller support because both can rotate. Okay, that is connection to the outside world. Inside, then you must have only pin connection. Okay, allowing to rotate as we showed the joint already. Okay, the second very important scenario is that all forces must be acting on the joint, not on the member. Right? For example, it should go like that. It's okay. So basically what happened, how the floor, as we talk, hanging on to the truss. It doesn't connect all the time. It only connects through the joint, meaning the slab will be down here and it connects down up to the joint, leaving this member free of contact. Okay? Now be clear? The two condition has to suffix first. Because whatever we prove next rely on this fact. One, every single member has to be connected through pin joint. Two, there will be no forces acting in the middle member. The forces have to act on the pin joint. That is the reason that this structure will never be concrete. It will be steel, it will be wood, because the steel is quite light compared to the weight it takes. So we can assume that the weight is negligible, okay, to allow no forces on the member. Well, before we go on to the proof, let's talk about certain terms that you're going to see. It might be news, it might be old. If it's old, never mind. If it's news, then we know what we're going to talk about. Let's talk about distance first. Notice that there will be repeated span. Okay? So, in general case, we probably do that. For example, if let's say each span is 4 meters, right? We can write it like that, but it's kind of tiring. It's kind of, especially if it's the same span length. What happens is that they will count it. In this case, there are 6 of them. 1, 2, 3, 4, 5, 6. 6 span. Each span is at 4 meters. That will be the one they use, not the top here. Okay? And we understand it. That symbol means it has to be 6 span. Each span is 4 meters. Okay? If they are not the same, then don't do it. I'm afraid that can't be helped. Well, this truss, I think it's called Warren truss. This is quite a tough one to analyze. So we're going to leave it until later stage. Okay? Then notice that since we're going to have to name the nodes and we're going to have to name the members, there will be 2 numbering system going on here, and apparently, unfortunately, one person named it different from another. Okay, this one system, when they name the node, sometimes they put circle on it, right, signifying they are node numbers. The word numbers doesn't have to be numbers, it can be ABC as well. Right? Numbering meaning just putting them in order, that's all. Okay, it can be ABC, it can be joint ko kai ko khai ko kwai, it could be alpha, beta, theta, whatever letters you want to use. Anything that go in sequence. Okay? But of course, if you're going to run by a computer, then number would be nice. Okay? Sometimes they don't put circle, they just use just number. Right? Like that. Maybe 4, 5, 6, 7. For example. Right? What about there are 2 systems they usually use for the nodes, either with circle or not. Okay, the member they have two kind of system to name them. Notice each member will have two joint connecting at the beginning and at the end. Right? One system they use is that they call it by the joint. For example, that one is between joint 1 and joint 2. That one we will call member 1, 2. Okay, that's another system. That one is member 4, 5, between 4 and 5. Okay. The good thing about this is that they don't have to put the name onto the picture. They just give the name for the nodes, and the member will be named automatically. Okay? Some people like me don't like it. So I rather give the numbers to the member. And the system is usually they put in a box to signify that it's not a node, it is member. Okay? But there are different systems they're using. So from time to time, if you see the number and you're not clear what it is about, ask. Okay? If these two conditions satisfied, apparently we have to rediscuss the internal forces because it becomes a special case for the pin joint truss. So to prove it as a general case, I will pull out one member. Okay, it could be any member, it could be in any angle. Okay, if I pull it out, then maybe it might look that way. The joint connecting it is joint I and joint J. Could be 1 or 2, 3 or 4, 5 or 6, it doesn't matter. Okay? The inclination could be in any angle. But we know that if at point I is a pin joint, point J is a pin joint, top at I, they can take only two forces, no moment, correct? Pin joint. One would be, these two forces will be 90 degrees to each other. Right? So maybe we can represent the force acting on this member like so. Don't forget the second rule. The second rule said that then there will be no force on the member. Right? Therefore, there must be no force between I and J. It has to be only on the nodes. Correct? So we still obey the rule. Now, I will get rid of the truss for now. Right? The same element. Now, we learned that with this picture, I cannot prove any further, not really far, right? So what happened is that I know that if two forces acting on the same point, I could combine them, correct? Using the triangle to combine them. Then these two forces will combine to a force going about that way, correct? These two forces will go about that way, right? So maybe we represent it that way instead. Rather than shear and axial, we just combine them, represent it to two forces. That Fi is these two combined. That Fj is these two combined. Now, if we look at this is one thing that is in the first half reading. This is called two-force member. This picture cannot be in equilibrium unless Fi is equal to Fj, and they must be on the same line. If it is on the same line, meaning actually this theta has to be 0, and it will be in that picture only. Okay? I'm not going to prove it again. If you can't remember two force member, I suggest you do reading again. Okay, but that is already in the first half proof. It's also in the exam, apparently. Okay. Since Fi and Fj are equal, so I will just call them F. Okay. However, now we should notice that we are looking at the topic. We are talking about internal force, right? We cannot see internal force unless you start cutting it. Okay. So let's cut at any place. Let's call it any place at the x from I. It could be x from j, doesn't matter. It's gonna prove out the same. Once we cut it, the usual picture we should see. Point I would draw point I to where I cut, right? Point I to where I cut, distance is x. At this moment in time, we don't know anything about internal forces in pin joint truss. Well, let's assume we don't. Okay? So what happened here then? We have to assume full options here. three unknowns, right? The normal axial, the normal shear, and normal bending moment. Okay? The special thing will happen after this. Yeah, let's get rid of those. Look at that one. What happens if I combine the force in the V direction, in that direction? That F doesn't count, that N doesn't count. Correct? To be in equilibrium, it only means that that shear has to be 0. Correct? Don't forget, this is not a specific case. This is a general case. Meaning you can pull any member, the same proof will exist. What it means there, meaning in pin joint truss members there is no shear. We don't have to calculate shear. Okay, this is proof now. Again, if there is a force on the member, this proof will be wrong. Okay, but this is only exists because there is no force on the member. Then, if I take moment, then let's say take moment about point A. That is point A. F times 0, V times 0, N times 0. What does it mean? To be in equilibrium, moment must be 0. There is no bending moment in pin joint truss either. Left with 1. Sigma F in that direction will get F equal to N, N equal to F. In other words, N axial force is not 0. Or at least it doesn't have to be. It could be in some cases, but it doesn't have to be. This proof shows that if all connection is pin joint, including the support, pin type, including support, and there is no force acting on a member, only acting on the joint, there will be only axial force inside the member, which reduce our question, which reduce our unknown. Every single member, rather than have 3 unknown changing with point, you have only 1 axial force per member. Is that point accepted? If so, then let's move on a little bit, okay? Because that is about it really. Now, what happened is that they said, I honestly don't know why they call method of analysis. It doesn't make any sense, but all the books said so, all the professors said so, right? Just to be on the trend with them, I will say so too, okay? Apparently, there's 2 ways to look at this analysis. They said one thing is that you look at the joint equilibrium, meaning you analyze how the joint can be in equilibrium, and they call it method of joints, or sometimes they call it joint analysis, right? It's nothing, it's just sigma fx, sigma fy. Well, my guess is someone want to have his name in the paper and with the book and so on, the call it method, so be it, okay? Sometimes, because the time is very long, looking at one point and at many points, this type of analysis, sorry, I forgot, it actually calculates equilibrium of joint, one joint to another, until you complete all the analysis, all the joints, okay? However, sometimes they said, well, sometimes you just want to know certain numbers, certain members, then what they do is they cut sections out, and then they analyze the equilibrium of that section, okay? And that is called method of section or section analysis. That's it. Next, we're going to see how it works, okay? But mark the word, remember the word. Equilibrium of joints, or, and slash or. You can use the 2 techniques together, right? And slash or section analysis, okay? Depending on which equilibrium you're looking at. Let's see example. This is a kind of pin joint truss. When you see the amount of member, you realize how happy you are to know that there is only 1 internal force per member. If this one have shear force diagram, bending moment diagram, you probably start crying, and me too. Okay, so at least let's appreciate the fact that there is only 1 per member. Okay, so let's go. Basically, in this case, they want us to draw or to find out, not draw this time, to find out all forces inside this member, 5 members. right? We already proved that there's only one internal force per member. This kind of question require 5 answers, right? Axial force member 1, axial force member 2, blah blah until axial force member 5, N1 to N5 per se. It's still internal force. So maybe we talk about, usually if they ask you to calculate all the internal force and the picture is not so big, generally you can guess that it's going to go by joint method, okay, analysis of the joint. Okay, still internal force. In this case we need reaction, right? Normal, you have to support pin joint, pin support on the point 3, 2 reactions, roller support on point 4, 1 reaction. In this analysis, it is very helpful to analyze which direction the force go first, because these things will be repeated use, meaning you calculate it, you're going to use it again. If you calculate negative all the time, it causes more problem. It's easier if you analyze the direction first and keep calculating positive. We have 3 reactions. How do I analyze without calculating? Can you tell me R3Y? Which way should it go? Left or right, and why? There is only one acting force in the x direction, correct? That force is 4AT going to the right hand side. There is no other reaction apart from R3X to resist it. So if 4AT go right, R3X have to go left. How can I tell R3Y then? No, this one. How can I tell this one? Oh, I changed my mind. How can I tell R4Y first? Then probably easier. R4Y, usually if the force on the same line, usually we go for moment equation, right? The way you analyze the direction is the same as calculation. So we go for moment equation. We take moment about this point here, point 3, to eliminate the need for R3X and R3Y involved, right? That 480 going clockwise. That one for 240 also go clockwise. That force has to force the structure to go anti-clockwise. In this case, it means must go up. Correct? So I can tell that one go up. Right? Now we are not so sure whether it's go up. Well, I'm quite sure it's go up more than 240, but never mind. Just for the point of thinking. If I really want to know that one, I could take moment about 0.4. In that case, that 1 times 0, that 1 times 0 as well. That 240 also times 0. Take moment about 0.4, the 480 going clockwise again. Therefore, R3Y must go anti-clockwise, meaning going downwards. Okay? So in this case, if you keep analyzing it, most of the time I hope, you end up positive number, meaning you get the right direction all the time. Sometimes it can't be helped, then never mind, but usually it could. Once we get direction, we just use normal equation. Notice that the calculation follow the way you analyze the direction. Like sigma moment at point 3, we get R4Y. Sigma moment about point 4, we get R3Y, and then sigma fx, we get R3x. General. Now, let's look at the free body diagram first. I hope this one is okay. Right? Can I move on? Don't look so confused, please. Okay? Not yet. That is the free body diagram with all the forces. Now, if I'm going to look at the joint, okay, notice that I'm going to have to pull out, if I study the equilibrium of the joint, then I have to draw the free body diagram of one joint at a time. Correct? Now, if I, for example, draw the free body diagram of point 3, of joint 3, of course there will be these 2 forces acting on it, right? And then I will have to have these 2 internal forces. Correct? Notice that the joint is just a dot. In fact, the side doesn't get involved. In this case, it means that we are looking at a particle, not a body, if we look at the joint. If we look at the particle, it means that it's only Fx, Fy, no moment involved. Two equations. So if I look at joint 3, I'll be okay, because I have two unknown, I have two equations. Correct? However, if I look at joint 4, I have a problem. Because joint 4, I have 600 going up, I have N4, correct? I have unknown, N3 unknown, and then N5 unknown. 3 unknowns, right? Again, joint 4 is just a particle, no size. Sigma Fx, sigma Fy only. Sigma moment will give you 0 equal to 0 all the time. It doesn't help, okay? So, in this case, it means that you should look at a joint that has only 2 unknowns at a time, okay? For example, in this one, you can start from joint 3 or joint 2, it's up to you. For no other reason, but I want to choose it, I'm going to choose joint 3, okay? So now, if I choose joint 3, then I have to draw a free body diagram for joint 3, right? That's the body, the 2 force apply, and then the 2 force unknown, right? Let's talk about this unknown one by one. Okay, let's talk about N1 first. I know that N1, because it's axial force, then it has to be on the same line as the member, correct? This member here is vertical. Therefore, N1 also vertical, correct? I don't want to put in the picture yet because I want to ask you that in this picture, does N1 go up or does N1 go down? Again, I want to analyze the direction before I start calculating. Is it going up or going down? Up. If it go up, don't forget axial force is tension compression, it's not up down. If N1 go up, is it compression or is it tension? Tension. Meaning, if we calculate positive, we will get tension. If we calculate negative, we get compression, right? N2, we could analyze the same way, and then, or N4, sorry, not N2, that one is N4. That number should corresponding to the number of the member. If it's member 4 and you call it N2, it will be really confusing, I think, okay? So please make sure that they're corresponding. Then you see the picture, you can guess what happened next, sigma Fx, sigma Fy. Then you get the 2 internal forces. Okay? Now because we're going to keep using that picture, now we analyze that, must go mark it there. Right? So it means that now my joint 4 doesn't have 3 unknowns anymore, right? Because I know N4 already. So at this point in time, my joint 4 has 2 unknowns solely, right? My joint 1 also 2 unknowns, my joint 2 also 2 unknowns. Which way do you want to go first? You can choose now. For one reason about the analyzing the direction, I will do joint 4. If I have to just work it out, I probably go back to joint 2 first and see later. But this one here, just so that we can discuss about thinking about the direction of the force, then I go to joint 4. Okay? Joint 4. So that's the picture. Now N4 in blue, we know N4, we calculated already, right? Tension then is going out of the joint. That is reaction R4Y, right? In this case, we have these 2 forces, right? Let's talk about N3. Why do I talk about N3 first? This one is vertical. That one is also vertical and horizontal. Meaning in vertical you can't analyze it first. But that one is in horizontal. That one is in horizontal. We can analyze it straight away. Right? So in this case it means that N3 has to go to the right hand side. In this case it means down and right. Correct? In this arrowhead. There. Correct? Yes? Okay. Then we know if it's going that way, tension, coming that way, compression. Okay? In this case, it means that if we calculate N3 positive, N3 is not tension, N3 must be compression, meaning we put in the right direction. If it's negative, it becomes tension, right? Again, it always go against your assumption. Okay? Then next is that one. You think it's up or you think it down? Up, apparently you can't really tell, because that one down, that one up. It depends on whether that down more or that one up more, right? But I think it's down too. Okay, so I assume it down. If it down, it's then compression still. Then again, this one here, sigma Fy first doesn't help, right? This one has to be sigma Fx first. Again, the order of analyze, of actually calculating, is the same order you actually analyze force direction. Okay? Therefore, sigma Fx first, and then because we know the angle, and then we can do sigma Fy, and apparently N5 is positive. Positive meaning we assume the right direction. In this case, it's not really down, it is compression. Okay? Once we got that, we update it. Because we're going to keep on moving. This time I will go for joy 2, I think. Yeah, joy 2. Okay? Something strange happened here. That is the free body diagram. We know 240, we know 480. We work out N5 already. We already doesn't know N2 in this picture. But we have two equations. Right? That is going to be normal case. If you run the joint method properly, you tend to have three equations left. Okay? One here. At the moment, we have one equation here and two here that we haven't used yet. Okay? That is usually we use for the check. Okay? So the first equation to find N2 first, and then we start checking. This is the first equation, sigma Fy 0. If it's 0, then it's okay. If it's not 0, it is not okay. No guessing, please, no guessing. Calculate it, because this is for check. If you're gonna guess, don't bother writing. Okay? So if you're gonna write it down, check it. Usually I suggest in the exam situation, you don't check it unless you have time left, or unless you want to make sure you get marks there, then you check. Okay? But it's up to you. Now, I have sigma Fx, sigma Fy here. If I draw or update that one first, as usual, notice that we have all the member forces, right? But we haven't actually analyzed joint 1 yet. So these two equations will be for checking only. Okay? No other forces apart from internal force of 3 of them. Sigma Fx work out 0, fine. Sigma Fy work out 0, fine as well. Okay? So that's it. That's the answers. Well, at least you don't have to draw a graph. Any questions on this one? No? Okay. There's another truss, a bit bigger. The question doesn't ask from all the member force. The question asks for only member A, member B, and member C. And it's only give three names. Usually this kind of truss, when you need to know only certain members, not all. Or sometimes you can, even though you need all, you can do section method. This one here, section method will be quicker. I will compare later. Okay? Well, first thing first, we have to agree first. Oh, we need reactions anyway. Now, before we actually start analyzing it, from this point onwards, I like you to consider your objective for a little bit. Now, the word section method means I will cut it through here. Notice that there is not a point anymore, it's the whole body now. Correct? So I still have sigma fx, sigma fy, sigma moment back. Right? Now, if I cut this picture here, then I can look at the right hand side, I can look at the right hand side, my choice, right? If I look at the left hand side, I need to know R1x, R1y, otherwise I can't calculate it. Correct? But if I look at the right hand side, I only want to know R2y. What I'm suggesting here is that to analyze this question, I only need one reaction, which means R2y. If I choose the right hand side picture after the cut. Okay, there we are. The mesh sort of section, then I only need one side. Sigma moment about 0.1 will give my R2y straight away, and then I will start cutting it. Okay, if I cut it here, what happened? Look at the right hand side, I will see this body. One known force, sorry. Each member we cut, this is a pin joint truss, therefore I will have three unknowns going up, correct? NA, NB, and NC. Axial force member A, axial force member B, axial force member C. The line of the force will be on the same line as the member, so the line of the force will be on this line. Again, I like to analyze the direction of these forces first. Notice on the vertical, apart from the acting force, there is only one unknown force, correct? That unknown force is on this line, is actually NB, meaning that force has to go down. In that case, it means down and to the left hand side, correct? So NB will be that one, which we call tension, correct? Now, well, let's go for that one below here, the one here, NC first, because apparently NC analyzed easier than in NA. NC, if I want to know NC direction, I have to eliminate the need for NB and NA, right? So I take moment about this point here, which I will call point 3. If I take moment about this point here, that's 700 push up, causing anti-clockwise rotation. To go against it, NC has to cause clockwise rotation, meaning it has to go to the left hand side. There we are. Right? How do I analyze direction for NA then? 2. I can use sigma fx. This picture is quite clear, right? Because if I analyze NC and NB correctly, these two forces go to the left. Therefore, NA has to go to the right. Okay. What about if it's more complex? This is probably, I don't want to use NB and NC. So I will use moment again. To eliminate the need to use NB and NC, I have to find a point where NB times 0, NC times 0. And apparently that point is here. So I will name that point, point 4. If I take moment about that point, NB times 0, NC times 0. That one cause anti-clockwise moment. That one has to cause clockwise, meaning it has to go to the right hand side. And that's what we call compression. Because it's 4 meters and 4 meters, that angle is 45 degrees. Right? Let's put in the distance. And then the rest we just follow the way we analyze it to calculate it. Sigma Fy, sigma moment about 0.3, sigma moment about 0.4. We are not so sure whether it's correct or not, so maybe we use sigma Fx to check it. Right? Sigma Fx equals 0, calculate it. This picture happened to get 0 equals 0. Then we are safe, it's okay. And that will be the answers. Apparently, The way we calculate this one is actually easier, usually less process than the shear force diagram bending moment diagram. However, I don't like it. It requires little understanding. It only needs hard work. Sine, cosine non-stop. Okay? Anyway, have a break first and then we come back to second hour and have fun then. Okay? See you in a bit. Believe me, the truss you're gonna analyze will be nowhere near the size of the truss you actually have to work on when you graduate. This is just a small one. Actually, we don't build this small. We big, much smaller. Okay, so this is just for practice. Well, go up to the gymnasium and count the members on the truss, on the roof truss. Those are the normal amount that we have to analyze. มันจะมาทีละจอยกันนะคือเรียกว่าที่วาดกลมๆให้รูปซ้ายมือหนึ่งมีไว้ให้ดูเฉยๆว่าเราคำนวณอะไรไปแล้วบ้างแต่รูปที่เราคำนวณกลับไปพอเราเรียนแค่เราจะวาดแค่จอยเฉยๆจะดูมีแรงอะไรทำที่จอยนั้นบ้างเพื่อศึกษาอิทธิพลของจอยนั้นจะหาได้ว่าแรงในภายในที่ตัวเองเท่าไหร่ Okay guys, I think the time is up for today. Homework this week will be only one question because there will be two from last week as well. This week I will assign the frame homework. Okay, the shear force diagram milligram for the frame. The homework for Truss will come next week. Okay, but then you will add on with homework from next week too. Okay, and then we just keep chasing all the tails. Now, I will try to release the exam marks within Friday. Likely to be Friday at about 4 or 5 o'clock. Otherwise, it will be on Saturday on the Facebook.